Hi, good morning everybody. We are again back with rate processes. So far we have talked on many aspects of rate processes. Last time we talked about solution reactions like we discussed some of the aspects of this metal reactions. Typical metal reactions are solvation and also solvent exchange reaction, okay, and also electron transfer reaction. So today we would like to concentrate on kinetics at electrodes. So what is an electrode? Now electrode is perhaps all of you heard about this electrolysis. Okay. So suppose you have got pure water, distilled water, and you have got two metal pieces like two copper rods. These two are dipped into water, and in that water you add from outside some sodium chloride salt. Okay. So and you pass current through this solution. So what do you expect? Now the expectation is that some reaction is expected, chemical reaction of course is expected. So when you have not added anything, I mean just pure water, and you dipped two electrodes, then if you measure the current that is passing through this circuit, that will be very small because conductivity is very less. Now the moment you add some salt, then its conductivity increases. As conductivity increases means some kind of some transport phenomena, transport of charge, transport phenomena is there, as a result of which this you observe some conductivity. Okay. Now the point is what is the role of these electrodes? Now electrode is a medium by which electrons can flow into the solution, or maybe electrons can be extracted. I mean electrons can come from the solution to the electrode and complete the circuit. Okay. So electrode, and also perhaps you heard about this electrochemical cell, or maybe simple cells like say where you get electricity from. Okay, like in one case say platinum hydrogen electrode, and the other case is saturated caramel electrode. So when these two electrodes are, I mean half cells are combined, you will get some electricity. Okay. So it's a medium by which you can inject electrons into the solution, or you may get. Okay. So that is it is basically the electron transfer in the electrodes, that is transfer of electron that is occurring at the electrodes. Okay. Now let us look at the interface of electrode and solution. Always you remember that interface is the region of interest in many cases. Okay, because interface means it is the region of inhomogeneity. Suppose if you have a solution of something, maybe say surfactant dissolved in water, then inside and suppose the concentration is less than its critical micelle concentration, then you may not expect any micelle in that solution, and what is happening in the bulk, it is homogeneous, but as you move on slowly towards the surface of this liquid, that is surface of water, then inhomogeneity, there is a region of inhomogeneity starts in, and at the interface you have got, in one side you have got aqueous phase and the other side you have got the vapor, and maybe these surfactant molecules are oriented in a definite fashion depending on its charge nature and also depending on its tail. Now, when you dip an electrode, I mean a metal piece, okay, say platinum, in aqueous solution of some electrolyte, then what is happening, let us try to look at. So, interface of electrode and solution. So, there is formation of electrical double layer. Okay, electrical double layer is like this, that you have got this metal part and this is your solution side, and this is the interface between your metal and the solution. Okay. So, plus charge may be accumulated over here and minus charge is also here, means this plus is attracted by another minus, this plus is attracted by another minus. So, as a result of which you have got a layer of plus charge and a layer of minus charge. It is called electrical double layer, which is formed when you dip a piece of metal in, say, in a solution containing electrolyte. Okay. And as a result of which there is some electrical potential difference is created. Okay. So, it is having positive potential, it is having the negative potential. Okay. So, if this is potential for the metal, say phi m, and this side is the solution side, then you may be expecting that something like this. So, this is your metal, then just at the interface, that is where metal just stops, means there is nothing beyond this point. Okay. Then it gradually decreases. Okay, this effect of this plus charge gradually decreases, and ultimately at a certain point it minimizes and then it remains flat. So, this point is called the outer Helmholtz plane, and this is based on the Helmholtz double layer model. Okay. So, this side is the distance from the electrode surface. Okay. So, electrode surface is this 0. So, distance increases. So, it is decreasing almost linearly. Okay. So, phi m is the metal potential, phi s is the solution potential, and it minimizes at outer Helmholtz plane. Okay. So, that is as if when the metal is dipped into solution, then it loses electrons, and that electron is gained by, that electron is gained by the solution. Therefore, this gains a positive potential and this gains a negative potential. Okay. So, this is the pictorial representation of that. Gouy-Chapman double layer model, there is another model. This model explains why measurements of the dynamics of electrode process are almost always done using large excess of supporting electrolyte. Okay. Whenever you measure something, I mean dynamics of electrode processes, that is done in almost all the cases in presence of excess of supporting electrolyte. Okay. Now, the earliest model of the electrical double layer is usually attributed to Helmholtz, that is I talked about, that is the Helmholtz double layer model. Okay. Helmholtz treated the double layer mathematically as a simple capacitor. Okay, it is a capacitor. You see, like there is a plane of plus charges, a plane of minus charges. Okay. So, it is simply a capacitor based on a physical model in which a single layer of ion is adsorbed at the surface. Okay. Later on, Gouy and Chapman made significant improvement by introducing a diffuse model of electrical double layer, in which the electrical potential decreases exponentially from the surface to the fluid bulk. Okay. So, here it decreases almost, see it is shown to be linear decrease, but later on Goy and Chapman introduced a newer idea, that it introduced a diffused layer, okay, that is this phi m reduces exponentially with separation, and here this is called the diffuse double layer. Okay. Here double layer is compact, but here the double layer is diffused. Okay. It is basically as you have reached the bulk where it is diffused, that is plus minus, but here they have they are not diffused, but they are some kind of tight. Okay. So, it is as if it is rarefied as you move on, away from away to a larger separation from your electrode surface, as you move to a larger separation. Okay. Now, this Goy-Chapman model fails for highly charged double layers. In order to resolve this problem, Stern suggested the combination of Helmholtz and Goy-Chapman models, giving an internal Stern layer, that is Helmholtz layer, and the outer diffuse layer, that is Goy-Chapman. So, it is a combination of this Helmholtz and Goy-Chapman. So, it is a mixture, especially it is for highly charged double layers, not for the simple cases. Okay. So, if you look at the Goy-Chapman model, you see that here at the electrode surface there is a excess of a positive charge, okay, and as you move on, means this way away from the surface of the electrode, there is some excess of negative charge, but that is going to be diffused, going to be lowered as you move on this way to a larger separation. Okay. So, for highly charged double layers, you have to think of a different model, that is a combination of Helmholtz and Goy-Chapman, and it is introduced by Stern. Stern model of electrode solution interface. You see here very close up to outer Helmholtz plane, it is behaving like Helmholtz double layer, and beyond that it is Goy-Chapman. Okay. The Helmholtz model overemphasizes the rigidity of the local solution. Okay. The Goy-Chapman model, for the Goy-Chapman model the rigidity is not that important, and improved version is your Stern model, as I talked about. Okay. So, here it is decreasing almost linearly and then exponentially up to the diffuse layer. Okay. So, this is what the Stern model talks about. Okay. So, again if you go back, this is your Helmholtz layer like this is Goy-Chapman, okay. Then it is combination of these two. Okay. So, this is Helmholtz and then this is Goy-Chapman. Okay. But the thing is that Helmholtz model overemphasizes the rigidity of local structure. Local structure means here they are thought to be very rigid, they are not at all mobile, there is not much rearrangement happening. But Goy-Chapman model, since it is diffuse kind of thing, so local solution rigidity, rigidity of local solution, it is not that important. Now, the interfacial electrical potential, let us think of that. What is an interfacial electrical potential? It has got three parts. I mean, you have to think of three things: outer potential, the inner potential, okay, and the surface potential. Okay. So, interfacial, if you think of interfacial potential, then you have to think of three things. So, this is your electrode, this is your inner potential phi, this is your outer potential, then it of course decreases. Outer potential, I mean electrode outer potential is this, it remains flat for some distance and then it reduces. So, this gap, I mean this difference is your surface potential. The potential difference between the points in bulk, that is metal, and the bulk solution is the galvanic potential difference, which is the electrode potential. I mean which may be regarded as the interfacial electrical potential. Okay. So, outer potential, the inner potential, and the surface potential. Okay. The connection between galvanic potential difference and the electrode potential. Now, electrochemical potential is the combination of chemical potential and electrical potential. So, this is your chemical potential and this is your electrical potential, that is as a result of this phi, and this is the amount of charge. I mean this is the charge on the metal. Maybe if it is silver, then it is 1, if it is other, say diamond, it is 2, and so on, and corresponding potential is phi. So, mu tilde is equal to mu plus ZF phi. So, it is the electrical contribution because of the thing I just talked about, that is whenever you dip a metal, then electrons are lost from the metal to solution, and as a result of which there is a potential difference generated. So, it is called the it is the electrical potential. Okay. So, this electrical potential combination with your chemical potential gives rise to electrochemical potential. Okay. Now, let us look at the rate of charge transfer. Now, rate of charge transfer, it is expressed through flux of products and the amount of material produced over a region of electrode surface at some interval of time divided by the area of the region and the duration of the time interval. Okay. So, it is expressed in this way: the amount of material produced over a region of electrode surface at some interval of time divided by the area of the region and the duration of the interval. So, rate law, product flux is equal to K into species concentration. And now, if we think of reduction process, if we think of reduction process, then rate of reduction, if you think of reduction process here. So, for the reduction process, reduction of oxidized species to a reduced one. So, it is V ox, I mean rate at which this oxidized species is depleted is Kc, because cathodic, okay, rate constant for the cathodic process. Cathodic means reduction times ox concentration. In the same way, the rate of oxidation of reduced substance is V red, which is equal to K anodic into reduced species concentration. Okay. Now, how to express current density? Current density for this. Okay. So, cathodic density is equal to Faraday into Kc this into this one, oxidized species concentration. Okay. So, this is Faraday. In the same way, anodic is like F into Ka into red, where in this case the process is reduction in this case is process is oxidation. Then what is the net current density? So, net current density is the difference between anodic and cathodic, okay, anodic current and cathodic current. So, which is equal to F into Ka red minus F into Kc ox. Okay. So, rate law says that the product flux is K into species concentration, and for the respective process, whether it is reduction or oxidation, we have to write the respective expression, that is V ox is this, V red is this, then current densities is expressed in this fashion, okay, because current density will be proportional to this rate and times your Faraday, okay, will give you the current densities. Okay. So, net current density can be obtained in this way. Next is free energy of activation. From the activated complex theory, we can directly write this, that K is equal to B into e to the power minus this delta G activation divided by RT, okay, and the corresponding net current density, that is J, okay, is F B A red into e to the power minus delta G A divided by RT minus this quantity. Okay. So, it is the pre-exponential factor. Okay. So, in terms of activation energy, we can write in this way. The activation energy is for the cathodic and anodic process. The anodic process, this is for the cathodic process. So, activation energies may be different, that may not be same. Okay. Okay. So, rate of charge transfer can be expressed in this way. Of course, in terms of activation, free energy of activation, we can write this way. Okay. Next is we will concentrate on Butler-Volmer equation. There is another equation. So, variation of galvanic potential difference across the electrode and solution interface. Okay. So, this is your metal, this is your solution phi m, phi s, this is your outer Helmholtz plane. So, this is the potential function as a function of distance. Okay. So, this is phi m, this is phi s, and with distance it follows some curve. Okay. Now, for process we can think of various curves like this. This is your anodic one, maybe it can start from here and giving rise to this one, and I mean this is your cathodic activation, this is your anodic activation. It may be different. So, the cathodic is delta G C0 is plus F delta phi. So, it is the potential difference. So, F delta phi. So, in this way you can write. Okay. So, the point is there may be other options basically. So, net we can write the free energy of activation for the cathodic process in this way, and for the cathodic process with proper this alpha is another factor which lies between 0 and 1, and for the anodic process you can write in this way. Okay. So, what this is your activation, okay, and this is your when this delta phi is 0, when potential difference is 0. Okay. So, net current density we can express in this way, that J is equal to F into anodic pre-exponential factor into reductant concentration times these factors times these two, okay, because we have to write, I mean we have to write this in this way, because we can write in this way, delta G C is delta G C 0, I mean of course double dagger plus F delta phi. In the same way G A you can write, delta G A you can write in this way. So, you just plug in these two over this expression, over this expression. Just plug in the information over these two expressions, because you have to express this activated one activation, delta G activation for the cathodic and anodic in terms of this figure. Okay. So, this is your cathodic delta G activation, of course 0, and this is your anodic, and this is your cathodic delta G double dagger. Okay. So, we have got this expression, okay. And now let f, okay, f is equal to f by RT. Let us write another quantity f by RT. This f by RT, f is a constant quantity, RT as long as T is constant is a constant quantity. So, f is equal to f by RT. We just write in place of f by RT by this. So, JA anodic flux, and this is your JC is the cathodic flux. We already have explained what is flux, current density. Okay. So, current density JA is this for your anodic, and for your cathodic is this. So, difference net current density is JA minus JC. Okay. So, you just take the difference between these two, you will be getting the net current. Okay. So, you can try calculating the change in cathodic current density at an electrode when the potential difference changes from phi prime to phi. Okay. Not delta, it is a typo. So, phi prime to phi, what is the cathodic current density? You can cathodic current density. So, this is your cathodic current density. Okay. So, just delta phi, if the value of your potential difference changes from say delta phi to phi, prime to unprimed. Okay. So, you just try to find out the value corresponding to delta phi and another corresponding to only primed and only phi, and you should be able to have some idea of what is going on in the cathodic current when it is changing from some value to other value. Okay. Next is calculate the change in anodic current density when potential difference is increased by 1 volt. In that way you can also find. So, this will give you the idea of how this is changing, this is changing. If you change delta phi to some value, or maybe some value, or maybe exactly some value like 1 volt. Okay. How this is going to affect your cathodic current and anodic current density. Okay. Next is overpotential. There is another aspect which is very important, that overpotential. What is, first of all we have to know what is overpotential. Okay. Now, when a cell is balanced against an external source, the galvanic potential difference can be identified as electrode potential. Okay. So, think of the Pogendorf's compensation method by which we can measure the electrode potential. So, in that case you have to have the cell balanced exactly. So, internal potential and the external potential, the current flowing is 0. Okay. So, under that condition perfect reversibility is reached, and the corresponding galvanic potential difference can be written as the electrode potential. Okay. So, specific condition that you have to think of whenever you try to find out the electrode potential. Next is when the cell is producing current. Okay. So, producing current means some reaction is going on. Okay. The electrode potential changes from its 0 value to E. 0 value zero current value E to a new value E primed. Okay. So, when the cell is exactly balanced against external source, your zero current value is say E, that is the equilibrium electrode potential. Now, when you draw electricity, draw some electricity, then what is going on? Then your value of E changes because it is no longer balanced. So, potential is changing. Okay. Now, then the difference between this E and E primed is the electrode's overpotential. Okay. And it is denoted by eta. So, eta is nothing but eta is equal to E primed minus E. So, it is the potential when it is producing current, and it is the potential when it is exactly under reversible situation, that is exactly balanced from against an external source. Okay. So, delta phi is n plus eta plus E. Now, if we express current density in terms of eta, then anodic current density can be written as like this, okay, and the cathodic current density can be written like this. Okay. And where J0 is a is a quantity which is called the exchange current density. Okay. When Ja is equal to Jc, then you can have exchange current density. What is the the value of the exchange current density? When cathodic current and anodic current, these two match, then you can get the exchange current density. Okay. Now, then upon plugging in this information, these two, that is net current density, to find out the next net current density, that is this is your net current density, J is equal to Ja minus Jc. So, you just subtract this from this. So, Ja minus Jc is this one. Okay, and this is called the Butler-Volmer equation, where J is equal to J0, J0 is the exchange current density. Okay. That is when J equal to 0, J equal to 0 means Ja equal to Jc, then you can get the exchange current density. Now, two situations may arise. One is low overpotential limit, when eta is less than 0.01 volt, and the high overpotential limit when eta is equal to or greater than 0.12 volt. Okay, these two situations may be there. Now, before that, the experimental diagram is this. You have got your it is basically a 3 electrode situation. This is your reference reference electrode, calomel electrode, reference calomel electrode. This is your working electrode, and this is your counter electrode. So, there are 3 electrodes. Okay. So, this is your current supply, this is connected to a source which is supplying current, and you have got your ammeter, ampere meter, this is your voltmeter, and this is a reference circuit. This constitutes the reference circuit. Okay, this part. So basically you are drawing a current potential diagram. Okay. So that is the experimental arrangement for doing this studies, electrode kinetics. Okay. Now, lower overpotential limit, let us think of lower overpotential limit. What is that? Eta is less than 0.01 volt. Okay. That is, eta is very small. So, F into eta is very less than 1. So, you can express your Ex in this way, that is Ex is equal to 1 plus x. Therefore, you just put this over here. Okay. So, Ja will become like this, and Jc will become like this. Okay. So, then upon expressing total current, this total current density which is equal to Ja minus Jc, which is equal to exchange current density times this one. So, that is equal to J0 F into eta. So, basically we see that net current density, which is nothing but equal to J0 into F into eta. Okay. So, the above equation is, so it is a linear relationship. So, therefore, J is proportional to eta. So, this equation illustrates that at lower potential limit, okay, when overpotential is very small, then the current density is proportional to the overpotential. Okay. So, this is very important, that under low overpotential limit we get this expression. Of course, with such approximation, means this approximation is valid only when it is very small. It is also important to know how overpotential determines the property of the current. Next is higher overpotential limit. Okay. So, previously we talked about lower overpotential limit, okay, and overpotential is nothing but the difference in this electrode potential changes from 0 current value to some new value when when there is some current flowing. Okay. So, you see that this is when this difference is very small, means I mean to say that lower potential limit means when this difference between E primed and E is very small, they are very close to each other, then and only then your current density is proportional to overpotential. This is very important. It is a very important conclusion. Okay. Next is what is going to happen when we are in the high overpotential limit, that is eta is large, greater than or equal to 0.12. Okay. Then it could be, overpotential large means it could be large in positive sense or large in negative sense also. So, when it is large positive, what is going to happen? That cathodic current density Jc is equal to J0 into exponential minus A f eta, and which becomes very small in comparison to Ja. Okay. Therefore, J is approximately equal to Ja, which is equal to J0 into e to the power 1 minus A into f into eta. Okay. So, if you take ln on both the sides, you will be getting ln J is equal to ln J0 plus 1 minus A f eta. Okay. So, under that condition, initially when overpotential is low, then there is a direct correlation, linear correlation between J, linear relationship between J and eta, but now it is, you see, it is a logarithmic dependence. Okay. It is a logarithmic dependence. Now, when eta is large, but it is negative, that is large negative. Okay. Under that condition, the reverse is happening, that Ja is much smaller than Jc, cathodic current, much smaller than Jc. Okay. Therefore, under that condition, when large but negative, eta is large but negative, then J is approximately equal to minus Jc, because J is equal to Ja minus Jc and J is much smaller, therefore, you can neglect Ja. Therefore, J is equal to minus J0 e to the power minus A f eta. If you again take ln, okay, so you will be getting ln minus J. Minus J means you are making it, taking a negative sign means it is not a logarithm of a negative quantity, but it is basically ln j. Okay. So, ln j is equal to ln j0 minus a f eta. So, here you have seen that when it is large bodies positive, it is 1 minus a f eta, okay, but here it is minus a f eta. Okay. Now, this is basically your the Tafel plot, that is the plot of logarithm of current density against overpotential is the Tafel plot. So, again let us go back to Bartler-Volmar. So, Bartler-Volmar you have got this from here, okay, here. Yes. So, Bartler-Volmar. So, Bartler-Volmar, from Bartler-Volmar you have reached, using the high overpotential limit, you have reached this graph, I mean this plot, that is logarithm ln plot of your overpotential, okay, and this is called your Tafel plot. Okay. So, when it is high overpotential, when it is low overpotential, then you get a linear relationship between j and eta, but when it is high overpotential, it is no longer a linear situation. Okay. Now, in general, exchange currents are large when redox processes involves no bond breaking, or if only weak bonds are broken, when exchange currents are high. Okay. And when exchange currents are small, generally small, when more than one electron needs to be transferred or multiple or strong bonds are broken. Okay. So, high exchange current and low exchange current, the situations are different. Okay. So, no bond breaking or formation is there when large exchange current, okay, but when small exchange current is there, then maybe one or more electrons are needed to be transferred, that is bonds are really to be broken. Okay. So, this is the general arrangement for measurement of electrochemical rates, as I told you earlier, that it is basically you do a current potential diagram. Okay, it's a arrangement for doing your current potential diagram. Okay, so basically, if you think of your Tafel plot or maybe your this Bartler-Volmar plot, everywhere you see that it is your you are plotting your current density. Okay, current density means it is basically difference of your anodic and cathodic. So, you are measuring the current density. Okay. So, in all cases, whenever you do some measurement on this electrochemical rate process, that is rates that is occurring at the electrodes, then you supply current from here. Okay, it is a source of electricity. Okay, there is a there is a counter electrode. Okay, there is a working electrode, and you have got your reference electrode. So, you measure with respect to your voltage is measured with respect to your reference electrode, that is how much of voltage is created, potential difference is created as a result of supply of current between these two. Okay. So, you are supplying current between these two. Okay. There is an ammeter. Okay. This is your working electrode, this is your counter electrode. So, it completes the circuit and you want to measure. So, this is the working electrode, means where the reaction is taking place. Okay. And you need a counter electrode to complete the circuit. Okay, and you have got your solution over here. So, actual electrode process is occurring, I mean in these two between these two. So, actual reaction is taking place over here, and because of the supply various electron transfer and other redox processes are occurring. Therefore, maybe your concentration, I mean concentration of certain substances, or maybe electrode is getting altered. Okay, so, electrode potential accordingly changes. Okay, so, you have to measure that electrode potential, how it is changing. In one case, whether as a function of time, that is how much time is required, or as a function of your current supply. So, it is a you draw a current potential diagram. Okay. So, maybe V, this is I, okay, current potential diagram you do. Okay. And from this current potential diagram you find out how this is changing, that is the functional dependence. Okay, that is the functional dependence of your potential. Potential changes means your electrode, I mean various electrode reaction is occurring. So, therefore, maybe because of the electron transfer, this electrode is getting either its potential is getting affected. Okay. So, this way you can measure, that is a rough sketch. Okay. In the next class we will talk more on this. There are various techniques to measure electrochemical rates, because it is the reaction that is occurring at the interface, okay, at the electrode. Okay. So, let us have a look at what we have learned so far. Okay. So, we have started with electron transfer in electrodes. Okay. Now, when it is the case of electrode, then the electrode has to be dipped into a solution of electrolyte. When an electrode is dipped into a solution of electrolyte, then what is going to happen, that the moment it is dipped, this electrode is losing some electron to the solution, therefore it becomes positively charged and the solution becomes negatively charged. Okay. So, one positively charged thing, another negatively charged thing, there is a possibility of formation of a double layer. Formation of double layer is similar to a capacitor. Okay. So, and Helmholtz actually introduced this idea, and his main idea was based on the model of a capacitor. And here is the plot of electric potential. We have already talked about that it is linearly changing with separation. Next, we talked about Gauss-Chapman model. It is they have introduced a diffused layer where the potential is reducing, changing exponentially with distance. Okay. And for highly charged double layers, maybe this model or maybe the earlier model is not sufficient to explain the behavior. So, in that case Stern introduced a combination of these two, that this is outer Helmholtz sphere, that is nearby portion is guided by your Helmholtz type of model and the outer portion is guided by your Gauss-Chapman model. Okay. Then you talked about interfacial electrical potential, that this is your electrode, okay. This is your inner potential, this is your outer potential, and this is the surface potential, which is nothing but the difference between these two. Okay. Relation between, we talked about the, what is the relation between chemical potential and electrochemical potential. Okay. So, this is your chemical potential, this is your electrochemical potential, where this ZF phi is the contribution from the electrical portion. Okay. Then you talked about the rate of charge transfer, and which is nothing but the product flux is nothing but the rate at which the electron is transferred times the species concentration, and we talked both in terms of oxidant and reductant, I mean oxidized species and reduced species, and current densities are expressed in this way, and net current density has been expressed in this way. Then we talked about free energy, talked about this current density in terms of free energy of activation. Okay, and we have used activated complex theory, and tried to explain this. I mean tried to improvise that, introduce that here. Okay. Then we got this Butler-Volmer equation, which is which is based on this calculation, and this Butler-Volmer equation is this, which relates your current density, net current density, with overpotential, where F is a constant. Okay. So, overpotential. Okay. So, this we expressed, I mean in terms of overpotential. Let us go back to the original expression, that net is this, okay, alpha or A, I means alpha or A. Here you see that this part, this cathodic part contains alpha, anodic part contains 1 minus alpha. Okay. This is your 1 minus A, means this is actually alpha. Okay. So, overpotential, we have then talked about overpotential. I mean we have discussed in terms of two case situations: lower overpotential, higher overpotential. Lower overpotential, this current density is linearly dependent on eta, I mean the overpotential, but for higher overpotential limit we get Tafel equation. Okay. And also we talked about this general electrochemical measurement. So, whenever it is the case of equilibrium situation that we do not get any electricity, then it is E, and when it is we are getting some current, then it is E prime. So, difference is basically your overpotential. So, when there is a flow of current, I mean we are getting something, some energy, that is cell is working, then reactions are proceeding. Okay. So, your current density, because of this various electrode processes like cathodic processes, anodic processes, your current density will change, and how this current density will change with overpotential, that we try to explain in terms of Butler-Volmer equation. So, that is a very important equation. So, in the next piece of lecture we will explore electrochemical measurements like voltammetry. Okay. So, that will be taken up in the next lecture. For this particular piece you may consult any standard electrochemistry textbook under the heading Electrodes, and maybe Bockris-Reddy's text will be useful, and maybe some internet resources will also be helpful. So, till then thank you.